Okay, welcome back everybody. Moving on to section 4.2, which is titled Fourier methods for solutions to second order PDEs, linear PDEs. And we're going to have to send our minds back to when we covered all of the Fourier analysis methods between the Fourier series transform, the Fourier series, Fourier's transform, etc. Because the whole reason why I introduced them in this course is because they're very useful for solving PDEs, in particular second order linear PDEs. There's something special about the interaction of Fourier methods with second order linear PDEs. And in fact, it was the heat equation that Joseph Fourier was trying to solve when he actually came up with his original series. So we're going to get into it, and I start with a remark. So I'm calling this a remark on the spatial boundary conditions of PDEs solved with Fourier methods. The reason I have this remark is that we have to be careful about what boundary conditions are allowed when we use Fourier methods. So when we were dealing with first order PDEs and we had the method of characteristics, we basically had free range with the boundaries so long as we satisfied the non-characteristic condition. We just didn't care about the values on the boundaries, it cared about the shape of the boundaries. With Fourier methods, it's considerably more complicated than that. So when we're jumping into higher order PDEs, not only have we decided to just jump into only linear PDEs rather than nonlinear PDEs like we were able to handle with the method of characteristics, but we also have to be extra particular about boundaries. So jumping up this one bit in order really makes our life harder, but these boundary conditions are somewhat natural. They're somewhat common for Fourier methods to handle, certainly for the Fourier transform. So we'll see that, but we have to add this caveat that the amount of problems we can solve when we get to second order linear PDEs has been greatly reduced because of how boundaries behave. And in particular with the Fourier series, the boundary, I'm going to mention this here, the boundary, I'm putting it in quotes, for the Fourier series is, I'm going to write it as a word and underline it, periodicity. That is what it means to be a boundary for a Fourier series. I've got it defined up here. This is one way to define periodicity. Why does this define periodicity for us? Well, it's saying if we start anywhere, x, and we move by an amount 2 pi, this should really be the period. When we move by the length of the period in any orthogonal direction to our axes, right? So we're dealing with in the event of minus pi to pi to the d power, that's how our Fourier series in higher dimensions was defined. So what is the length of that interval is 2 pi, and then the xj is any of these directions. That's the xj direction. So since we have this hypercube, the directions are the ones which are perpendicular to the surfaces of the hypercube. If we move 2 pi in any direction, we actually have to end up where we started. Okay, so moving 2 pi in any of the orthonormal basis directions puts us back where we began. That's a definition of periodicity. And this is a very nice mathematical way of representing that. Now we can interpret this notion of periodicity over such a hypercube as actually joining. We can imagine we join the edges of the hypercube together, and in one dimension, well, a hypercube is just the line interval, negative pi to pi. If I join this edge at minus pi to this edge at pi, imagine that's a string and I join them together. If I link those two together, what I end up with is the circle. Okay, so we can also think about the entire space, the one-dimensional space that minus pi to pi along with the periodicity condition is the same as a circle in the sense that a function takes values on a circle. You can imagine I'm trying to draw this as an up or down. So the function is taking values along the circle itself and nowhere on the interior. Imagine that it's just empty space between the circle otherwise. So the function takes values around the circle, on the circle is the inputs, and then it's really natural to think, okay, anytime I move, in 2 pi directions, 2 pi amount in any direction, I end up where I started. Even if I start here and I go around 2 pi, I end up where I started, etc., etc. Now, if we do the same thing with the square, right? If d was 2, then instead of having a unit interval, I have a 2 pi length interval, I have a 2 pi length square. So this is a width of 2 pi, and that's a width of 2 pi. And if you want to work along with me, It's not the easiest to do with the sheet of paper because of Gauss's theorem of Gregorian, which says that the flat curvature of the paper needs to stay the same. So you wouldn't be able to do it with a piece of paper very easily. But imagine you have rubber or something, a flat sheet of rubber that's in this shape. If you decided to grab this end and connect it to this end, okay, what are you going to get if you connect those ends together? Is you would get a cylinder. But secondly, if you decided then you wanted to grab your cylinder and then connect the flat ends of the cylinder together, what you end up getting is the two-dimensional torus, or donut, right? If I take a tube and I connect the open ends of the tube together, I will end up with the donut, or the torus. And so we have this name for really this space, minus pi to pi to the d power, along with periodicity, is called the d torus. D for d-dimensional. So if I did minus pi to pi to the 7th power, that would be the 7 torus. So here's the 2 torus. Here's the 1 torus. And we can think about, even with our 2 torus, we can think about a function with height, right? So at each point on this 2 torus, there's some height for this function. And so we'd want to draw it like a 3-dimensional shape, maybe. There's a function on the torus that has a very specific height all around the 2 torus, but once again, it's periodic, because if I start here, and there are 2 orthogonal directions, right? The one is towards the center of the torus, and the other orthogonal directions around the circumference of the torus. If I go 2 pi distance in either of those 2 directions, I end up where I started. So that's always going to be true of these higher dimensional tori. And in fact, right, this notion of minus pi to pi to the d, even though I was calling it the hypercube, when we do the Fourier series on this and reconstructing only periodic functions, we're really working on the d torus. So is the space within which the Fourier series works, okay, along with periodic. So that space along with periodic is the space in which the Fourier series works. So really all of our PDEs, if we're going to be solving them with the Fourier series, not the transform, but the Fourier series, we've got a finite interval, we're really allowing our PDEs to evolve on a torus. Any number of dimensions, but it is on a torus, which means we bring up the really important question: what is the boundary of these spaces? And these are the whole space. These are the omegas. Everything in red is omega itself. It's not that everything inside of it is omega. It's the red line, or I guess I'm inverting it for the video, so it's something like cyan probably. So the cyan color is omega. It is the domain of PDE, is the torus itself. What is its boundary? It doesn't have one. There is no boundary. Slash, you could think about periodicity as a boundary. It's the closest we have. So defining periodic says, kind of like there is a boundary, but it's been connected to itself. Or you could just say that the boundary is non-existent. But that means that you can't actually define boundary values for these problems. Boundary values don't exist when it comes to solving PDEs with the Fourier series. I shouldn't be 100% true about that, because I say without discussion of distributions, but in the absence of discussing distributions, which is something probably reserved for a graduate level course, we're not going to be able to have any boundaries when we're solving PDEs with the Fourier series. And that's okay. We just have to keep that in mind. When we get to the Fourier transform, things get a little bit easier, because the Fourier transform was not existing on the hypercube, it was existing on this sort of a space. It was existing on RD, right, a d-dimensional real space. And we just had the one condition on quote-unquote boundary, which the boundary on R is, infinity plus or minus infinity, and then d copies of that. Right, so whatever that collection of numbers is the quote-unquote boundary of the Fourier transform, because we can go infinitely far. Well, this integral saying that the integral of our solution needs to exist and is finite, if I square it, that certainly makes the following true. It must decay. The solution must always decay to 0 at the quote-unquote boundary. Okay, so as it goes to plus infinity, as it goes to minus infinity, in any direction, our solution is going to have to tend to 0. And in fact, this is actually stronger behavior than the solution tending to 0. There are functions whose height tends to 0 near infinity that the integral doesn't exist. So we do have boundary conditions for these sorts of functions as well. It can be handled a little more easily because when we think about physics, I got this mention of physics here. What is the probability of finding an electron an infinite distance from where it was once measured? That probability is going to be 0. There's a lot of physical phenomena that exist within some relatively small region of space when you compare it to an infinite amount of space. And so adding the restriction that whatever we're measuring decides to decay fast enough out to infinity is a pretty easy assumption to make. So the Fourier transform, when we're dealing with it over all of space, is not too bad to work with these quote-unquote boundary conditions, but we just have to keep in mind that if we use the Fourier series, we have periodicity. If we use the Fourier transform, our solutions decay at infinity, and that will hold some serious weight when we try to construct these problems and solve them. So before we actually get into solving, I want to make a discussion on something called Fourier multipliers. This is a really cool property of the Fourier transform, and actually it's a property of other transforms as well. But that's that we're going to have an ability using the Fourier transform, and I commented on this before. We're going to come up with an ability to write these expressions for the Laplacian, which you'll keep in mind is partial x squared plus partial y squared plus partial z squared, if you're in 3D, or x1 squared, x2 squared, x d squared, if we're in d dimensions, or however you want to think about the Laplacian, whatever number of dimensions you're in. These are, derivatives, partial derivatives, but we actually have a notion of inverting all of them. Of course, that seems somewhat natural that we're going to invert them using an integral, but when you have sums of partial derivatives squared, maybe it's a little bit more complicated, right? It's easy to think about the integral dx as like d dx inverse, which you could think about as, in quotations. Nobody tell me that that's actually being true, 1 divided by d dx. But if we think about it a little bit more interestingly, when we have partial derivatives, if I try to do something like 1 over partial x squared plus partial y squared, this is definitely not equal to 1 divided by partial x squared plus 1 divided by partial y squared, right? The distributive property doesn't really hold with addition, and so we can't actually think about this as integrals the same way. We have to be something a little bit more clever, even with the inverse Laplacian, but especially when we're talking about exponentials to a derivative, right? What in the world would e to the t d dx look like? And maybe if you've taken my ODE's done right course, you've probably seen me derive that as well. But we have ideas for what these sorts of objects might look like, but we want to make that formal, and we can do that with a concept called the Fourier multipliers. The reason why these would be important, because I emphasize all three of these over and over again, is that really we can think about phi being some sort of Laplace inverse of the function 0 would solve Laplace's equation, right? Because then delta phi would be delta of delta inverse of 0, which would be 0. Now, of course, we're going to find out that delta has to be a linear operator, so linear operator on 0, 0. We'll get to why that's maybe a bit of a problem later. But thankfully, these Fourier multipliers show us why it's a problem too. We can think about phi being e to the t delta of just an arbitrary function of x and y, right? Not of t, but of x and y. That's going to solve the heat equation for us. Because if we took a derivative in time of this expression, because f doesn't depend on t, all we're going to pull out is a derivative in double derivatives in space. That's going to be the same as the Laplacian of phi. And of course, that is your heat equation. And then finally, if we do a plus minus t to delta to 1/2, right? So the plus minus is coming from the exact same spot you would expect it to when you're taking a square root, right? A square root is going to dictate that we have a positive and negative term, which both solve this, because the square root can be both positive and negative. And that's going to solve the wave equation if we acted on an arbitrary function of x and y, because if we take two derivatives in time, that means I'm just doing two derivatives of that exponential, so I'm getting two versions of plus or minus delta to the 1/2, so plus or minus delta to the 1/2 squared, but that's just going to simplify to delta. So we get that d squared t is the same as delta phi, which is the wave equation. So if we can make these formal, then we have a way of solving our holy trinity of PDEs that we just derived in the last video. So what we're going to work on is making these formal using the Fourier methods. I'm going to start with this definition. I call it operator notation for the Fourier transform and inverse Fourier transform. This is very common. It's quite possible that you've already seen this notation before, but we'll use like a little calligraphic F. and calligraphic F inverse for either sending us into the transform space or pulling us back from the transform space. So I make this formal with a definition: calligraphic F on phi of the variable y, and actually I should mention this should also be the variable n in the first case, is equal to the integral of phi against the complex exponentials with the variable n, so long as we're on the periodic hypercube, or it's equal to the variable, or the integral of phi against the complex exponential in the variable y when we're on all of space. So second case, this is really your Fourier transform. First case, that's really your Fourier series transform. But we're just going to call that calligraphic F on phi. And then if I want to invert it, calligraphic F inverse on phi hat. Okay, now as a function of F, it's either the Fourier series, there it is, or it's the Fourier transform, the inverse transform, where I'm integrating over, one more typo, integrating over the variable y. Okay, so what this allows me to do, so I'm just going to think about calligraphic F and F inverse. I'm going to call them the Fourier transform and the inverse Fourier transform from now on. I'm going to think about them as objects that I can, or mathematical transformations which I can perform on mathematical objects. This is what allows me to define a Fourier multiplier. Because that's a transformation, and that's a transformation, what I can do is I can incorporate a function between the transformations of F and F inverse. Right, so what this function in the middle does is it changes the behavior of really the inverse, right? Because if ML, what I have here, if this function ML was just equal to 1, then I'm going to multiply my Fourier transform by 1, and then I perform the inverse and I end up exactly where I started. But if I use a function that's not equal to 1, that varies over space, over my transform space, then when the inverse hits everything, it's going to see something new. And whatever that new thing is, whatever it sees now is going to be what I call L. Okay, so if I have some function of the transform space, and I include it between F and F inverse, then I gain an operator on the regular space. And it turns out that the derivative will be one of these operators that I can gain. That's kind of the important thing here. In the event that this operator, the one that arises out of these functions, happens to be a partial differential operator, we actually will call this a Fourier symbol. It's often called, or just a symbol of a PDE. And so if that operator happens to be a partial differential operator, it's called the symbol of the PDE. But we won't use that terminology too much. We'll use Fourier multipliers a lot. And now this example is really the only reason why I've included this entire section in the book. The example is that the Laplacian is a Fourier multiplier, okay? So this delta being dx1 squared plus dx2 squared plus dot 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 plus dxd squared can be written as f inverse of a function of my space and then f. And this is going to be really important to us. So how can I see that this is true? Well, we've kind of already seen that this is true. Derivatives in Fourier space look like I n, right? And the Laplacian, so we'll say something like the gradient is I n, so the Laplacian, which is the gradient dot itself, should be I n dot I n. What would we know about i's? I squared is negative 1, n dot itself. So the vector n dot itself will just be the magnitude of the vector squared. And so the Laplacian, which is the gradient dot itself, is negative n squared, magnitude of n squared. Well, what does that mean? That means that that's in Fourier space. In Fourier space, it's a function. Anything that's a function in Fourier space is a Fourier multiplier. And so Laplacian is this Fourier multiplier where we have the Fourier transform multiplied by a function inverse Fourier transform, or equivalently m sub delta of n is negative n squared. Similarly, in the event that we're doing not the Fourier series, but the true Fourier transform, we get negative magnitude of y squared. So this example that the Laplacian is a Fourier multiplier is 100% the entire reason why the Fourier series is even included in any PDE's book. It's exactly this example. So we can use this to define the functional calculus. What do I mean by functional calculus? I mean to define this collection of operators. It's called a functional calculus because it's a calculus. We're performing, inversions, derivatives, etc., inside of functions, right? So the functional calculus is this manipulation of operators as though they were functions. And we can define it on any sort of Fourier multiplier, so it's not particular that we need to define it just on the Laplacian, but that's the useful one. We can define it on any Fourier multiplier. So any function we want to take, f, as a function, we can take a function of an operator. Maybe I'll mention that here. Function of operator is actually just the function of the Fourier multiplier. It's defined by that. Okay, this is not a theorem. This is a definition. So we define the function of the operator as actually the function of the Fourier multiplier, and then we keep f inverse along for the ride. This is what I mean every time I say that the Fourier transform diagonalizes the Laplacian or even the derivative. It's because, like, what does this look like? This looks exactly like matrix diagonalization. And if you go back to chapter 1, and we talk about how e to the tm is x, e to the td, x inverse, what do we have here? We have e to the t delta is f inverse e to the t negative t n squared f, right? So these are fundamentally the same sort of operation that we're performing. And this is what it means for the Fourier series to diagonalize an operator. It sends it into just a collection of numbers, which is the same thing as what a function is. So because of that, we can immediately construct the inverse Laplacian using the Fourier series. So the inverse Laplacian is just f inverse of 1 divided by the Laplacian, that's what's going on here, of f. Laplacian inverse is f inverse of 1 divided by the Laplacian. Well, what is 1 divided by the Laplacian? We just decided the Laplacian was a Fourier multiplier. 1 divided by the Laplacian of that times the Fourier transform itself. It's a function of the Fourier multiplier. What do you know? This c that's going on right here is a little bit special, so it's true at the case when n is equal to 0, and in fact this is because of the constant of integration, right? So we're trying to invert a derivative operator here, and so we're going to recover a constant of integration. Similarly, we can perform the exponential of the Laplacian, right? So I'm calling this the Fourier Laplacian exponential, where we just take e to the t delta is literally e to the t Fourier multiplier of delta, e to the negative t Fourier, or positive t Fourier multiplier of delta. Because the Fourier multiplier had a negative sign there, you pick up the negative sign for free. Similarly, e to the plus or minus t delta to the 1/2 is going to be e to the plus or minus. Then there's an I here. Why is there a plus or minus I going on? Let's be careful about this. Recall the Laplacian had a Fourier multiplier, which was negative magnitude n squared. If I'm going to take a square root of that object, I'm getting a square root of a negative 1. Okay, so delta to 1/2 has to be, there's a square root of negative 1 here, so I get an I, then I get the magnitude without the power of 2. So that's why there's an I there. The plus or minus are coming along for the ride. And then we can use these three, right? These are the three examples that we're going to solve our Holy Trinity. We can use all three of these examples to actually go ahead and solve the Holy Trinity. I'm only going to go through the first one today, and in fact, it's really a non-example. But then the next day we'll get through how to use these lovely identities to solve some of the Holy Trinity problems. So here's our non-example, which is that there are no non-trivial hypercube periodic or square integrable solutions to Laplace's equation. In other words, I'm thinking about this equation, delta phi equals 0. If I decide to add the periodic condition onto this, then the only solution is all 0. If instead of the periodic condition, I decided to add square integrability as my condition, then the only solution is still phi is 0. So there's really only one solution on these special spaces, and that's the 0 solution. The question as to why comes straight from this mean value property that we covered in the previous video. If I decided to look at the average of phi in either of these situations, the average of phi in either of these situations, the mean value property over a periodic space says that, well, everywhere on my periodic space, is equal to the average of everywhere else. okay, well, if I average over everything else, then I only get a constant. So everywhere it's equal to a constant. So it's super trivial in my periodic setting. In the case where it's defined over all of space, then I can just let R, this R right here, go to infinity, right? R can go to infinity over all of space, but since I decay, I have to be equal to 0 when I'm really, really far out near infinity, which means that the average value here has to be 0. And so you actually get only trivial solutions to the to Laplace's equation when we deal with the Fourier transform. The other two methods, like the heat equation and the wave equation, have some non-trivial parts. But anyway, we're going to save those for the next class. I'll see you then. Bye.